Hello, and welcome to another lecture in the course. This time we're talking about the Riemann sphere. So this is section 1.3 in the book. Now, what we do sometimes with real numbers is we extend them by adding plus and minus infinity to make the real numbers into this nice compact interval, which makes some arguments easier. You could just think of it as sort of making this what does it mean to go to infinity, plus or minus infinity, making it more concrete in terms of making an actual topological space underneath, and it makes you don't have to deal with infinite limits and limits going to infinity, as you don't have to do these differently, right? You can just you just treat it as a topological space. Now, similarly, what we can do is we can do this with complex numbers, and we're only adding one infinity here, and that's really because, well, for real numbers you have order, and everything is actually defined by the order. The topology, the taking of limits and everything, that's defined by an order on the real numbers, right? The plus infinity is something that's bigger than everything else, and minus infinity is something that's smaller than everything else. Now, that doesn't make any sense for complex numbers. There is no order, right? We're really defining, the topology on C was just the topology on R2 on the plane. There is no order. Now, for that reason, it doesn't really make sense to have multiple infinities for the complex numbers. It really makes sense to only have one infinity, because there is no something bigger than the, right? So that's the difference, is that there is only one infinity because there is no order. I mean, that's basically the reason. And we call this this set, C sub infinity, we call it the Riemann sphere. By the way, the notation, there is no really standard notation for the Riemann sphere. This is the common notation, C sub infinity. But you see different ones. You see C with a bar over it. You see C with a hat over it. A bunch of different things. Another notation that we'll see, I call it CP1 or P1 as it's the one-dimensional complex projective space. That's another way of thinking about the Riemann sphere. But we'll use this when we talk about the Riemann sphere, C infinity. Now, how do we define topology on this? Because that's really, we need to take limits. That's really the whole point of this, is to be able to take limits. So how do we define the topology? Well, we first define this bijection. So it's a bijection of the Riemann sphere to itself, and we make it if Z is neither 0 nor infinity, we take Z to 1 over Z, right? So we invert Z for every non-zero, non-infinite Z, right? Where we know how to do that. Now, if Z is 0, we take it to infinity. If Z is infinite, then we take it to 0, right? So you want to think of it as somehow, flipping everything on its head. We'll see that the Riemann sphere is actually topologically a sphere, and this is sort of this is a sort of a flip, if you want to. Actually, it's sort of two flips, so it doesn't change orientation, but we'll talk about more about that when we get to the linear fractional transformation next time. So, all right. So we get this bijection. Now, we want all the open sets in C to be open in the Riemann sphere. So we don't want the topology to be different when we're talking about a complex number, right? We only want to really figure out what happens at infinity. So the open neighborhoods around every complex number should be exactly the same as they were when you were just talking about C and not C infinity, right? So now, how do we define the complex the neighborhoods, the neighborhood basis around the origin? Well, around infinity. Well, we take the neighborhood basis around the origin, and we map it forward by this function g, right? So we take every neighborhood of the origin, right, and we push it forward by g, and that's going to be a neighborhood of infinity. We declare it to be a neighborhood of infinity, right? That actually gets us all the open neighborhoods of infinity. Well, maybe not all of them. There's one more. I mean, you always need the entire space, right, to be open, right? So that's the only one that you're not going to get in this way. Now the point is that if you define this topology on the Riemann sphere, then convergence at a regular complex number is exactly the same because the neighborhoods are exactly the same. Because we have just the normal topology nearby locally, right? And if we're talking about what happens at infinity, what we could do is we could use this map, this gene, this bijection, map everything to 0, and it's just regular convergence at 0, right? That's really the idea of this. Now, there's a way of picturing what the Riemann sphere is, and actually, a way of giving it a nice metric space structure, if you want, which is going to give you the same topology, by the way, right? But it's going to actually also give you a metric. It's going to be a different metric than the metric from C, and you can actually think of a couple of different natural metrics on here, right? So suppose that I have S2 is the standard unit sphere in R3, in 3 space, right? So that's a fairly standard standard notation for it's the 2-dimensional sphere, right? So just like the surface of the Earth, right? And it's radius 1 centered at the origin, right? It's just the surface, right? Just this 2-dimensional nice manifold. And we define a bijection between S2 and C infinity in the following way, right? So between the Riemann sphere. Well, first we have to put infinity somewhere, right? So, or we have to put map something to infinity. We're starting on the sphere. So we take the north pole, which is going to be 0, 0, 1, and we map it to infinity, right? So that's the first thing. And then for all the other points, for everything on the sphere that is not the North Pole, well, there is a unique line through the North Pole and that point, right? Because, well, now I have 2 distinct points. So there's a unique line through them, right? Just by basic geometry. And that line, right? I have a line, a 1-dimensional straight line that has to intersect the xy plane, right, in R3 at a unique point. Some point xy 0, right? The third component is supposed to be 0, right? Don't really, you usually say x, y, z, but a lot of times we, in this course we use z for complex numbers. So, this is really the only time that it would make sense to talk about z as a real number. But the third component should be 0, right? So basically, for any p in the sphere that's not the North Pole, look at this line and see where it has to intersect the xy plane somewhere, because otherwise, it would have to be tangent or parallel to the xy plane. But if you think about it a little bit, that's not possible. So it always intersects somewhere, And what we're going to do is we identify this, this xy0. Well, we can think of that as being a complex number if we think of the xy plane as being C, right? So it's x plus iy. And so then we map the point P into this x plus iy, right? I wrote as C over here, right? Now, here's the picture, right? It's always better with a picture. So here I have infinity, which is supposed to be the North Pole, right? So that's 0, 0, 1. It's this guy, right? So that should go to the North Pole, right? Then we have a point on the sphere that's not the North Pole, right? And we draw this line, right? And it intersects the xy plane somewhere, and we identify that point with some complex number C, and that's where we take this guy, right? So this will give you a unique, it's a unique point here, right? And you can go the other way around, right? I mean, if I have any point on the on the plane, I can draw a straight line, and it will clearly, maybe it takes a little bit of geometry. It will intersect the sphere, and you get so it is a bijection, right? It's a nice bijection, right? And so now, sorry, right? So now if you want to have a metric space structure, well, just take the metric space structure on S2, right? On the sphere, right? So the sphere is a nice metric space, and there's a couple of natural metrics on the sphere. So really, take any one of them. You could just take the metric from R3, for example, and that's going to give you exactly the same topology as before. Again, that would take a little bit of checking, but it's true. All right, now the point of defining the Riemann sphere is to allow basically to have certain limits to have value infinity, and also allow limits as z tends to infinity, and think of it as just any topological limit, right? So just think of the Riemann sphere as your topological space, right? Now, conveniently, the topology on the Riemann sphere is exactly what you would get if you do this one-point compactification, right? This is a fairly standard construction you can do with really any topological space. You can just add a point at infinity and make a compact set. Now, in this case, that's exactly what it is, but it's more than that, right? I mean, we think of it really as a sphere geometrically, but you get the same thing with the one-point compactification. And when we write limits, well, we just if we have a function defined some subset of the Riemann sphere, maybe it's just defined on some subset of C, right? And it's valued maybe in the Riemann sphere. Well, we define this limit in terms of this topology, right? That's the whole point. And so there are a couple of exercises what this means, right? If you want to write this down, if you want to translate what this topology would do if you didn't want to use the Riemann sphere topology, right? So first, well, I mean, if you have this L and this Z naught, right? If they're just complex numbers, then the limit in the Riemann sphere topology should be the same as the limit in the complex number topology, complex plane topology, right? So that's first thing. Now, second thing, well, suppose that you have L is some complex number and I look at the limit as z goes to infinity, well, that's, that should be the same thing as, if I don't want to write down, this thing was anything about Riemann sphere, I say that for all epsilon, there exists, so instead of a epsilon delta, right, we use something, instead of, delta being smaller and smaller, this is really going to be about some m being bigger and bigger, sort of going off to plus infinity as a real number, right? So there is some number m, real number, such that the f of z is within epsilon of L whenever z is bigger than m, right? So this, this guy, that will give you these neighborhoods of infinity, right? So that's if L is a complex number. Now, you could also think about, well, what it means to be, what if I going as a limit as I'm approaching some complex number, but I want the limit to be infinite. Well, that's bigger, again, just introduce this m, right? So that means that for every m, there exists a delta such that this this f of z is bigger than that m in modulus whenever I'm within delta of z naught, right? So you see how this just if I'm talking about infinity, I have this. If I'm talking about a finite number, I have this. And the same thing over here. I'm talking about infinity, I have this guy. If I'm talking about a finite number, I have this, right? That's basically, not quite the, because it's this is using the standard metric on C, right? It's not using this metric on the Riemann sphere. If it was using the metric on the Riemann sphere, it'd just be the metric there, right? All right. Now we can also think about this map G, and that this might actually be a more convenient way of computing these limits. So if I'm talking about a limit of something as z goes to infinity, and now think of L as sort of anything, either some complex number or infinity. So we say that this limit. This limit is L if and only if this limit as z goes to 0 is L, right? So I basically just look at 1 over z, right? So f of 1 over z, right? Because 1 over z should go to infinity as z goes to 0, right? And now over here, I can just think of, however I think of that limit, right? So if L is a complex number, I just think of, just the standard standard complex number convergence, right? Now, similarly, so thinking of what happens when I'm going to infinity, right? So now let z be anything in the Riemann sphere. So the limit is infinity if the limit of 1 over the function is 0, right? So this works, both on the sort of the source and the target, right? As it should, right? It's the same topology, right? So it's really about 1 over z, and that was we made that work, right? We created topology exactly so that this would work, right? Those are precisely, the 1 over z takes neighborhoods of infinity to neighborhoods of 0 and vice versa. So this should work, right? I mean, it's all set up so that this works. But that makes it easy to think of, infinite limits and limits as something goes to infinity, right? And you can always translate everything to 0, right? Now, if we're talking about some expression like 1 over z, it makes sense to just say 1 over z is equal to infinity when z is 0, right? Similarly, we could just talk about the value of z, right, as when z is infinity, the function z, the identity, is just infinity, right? I mean, that sort of makes sense, right? So we can think of that being defined at infinity, just like 1 over z is defined at 0, right? And also 1 over z at infinity should be 0, right? I mean, we're basically just taking the limits and, assigning the value to be the limits, right? Now, consider any polynomial, p, right? So polynomial of degree d, so the a1 through ad, or sorry, a0 through ad are just some complex numbers. We're thinking about this function. If d is not 0, right? So if we don't have just a constant polynomial, and we also want this to really be the degree of the polynomial, so we don't want this leading coefficient to be 0. Then it's an exercise to show that as we go to infinity, as z goes to infinity, p of z also goes to infinity, right? So sort of fairly standard fact about polynomials. And you've probably seen, a version of this in some, undergraduate analysis, and the proof is exactly the same. What you can do is you can, and it's an exercise to show this, but sort of a hint of how to do it, is to first show this sort of inequality for large z, right? So if I have a large z, I'm gonna show that I can really bound this guy in modulus from below by c of mod z to the d, right? And that one, this thing is easy to show that goes to infinity, and therefore this must go to infinity, right? And this, this c is not necessarily going to be this ad. It's probably going to be something smaller. Probably want to make, well, it should be, if this makes any sense at all, it should be a real number. So make it a real positive number, and should be smaller than the size of the AD, right? And you can do this. Right? Let's take half the size. Let's say that will work, right? And you have to, it's going to be for large enough z, so it's not going to be for all z. Because this p might be 0 somewhere even, right? So you can't do it for all z, but once z is large enough, you get this, and that's all you need for showing that what happens as the limit goes to infinity. Just need some, you need to know what happens for all large enough z. So for every non-constant polynomial, so something of a polynomial of degree 1 or more, I can just define its value at infinity to be infinity if I want to, right? So you can easily say p of infinity. What's p of infinity? Is infinity, and really we're just talking about this limit, right? Now, one thing to be careful about the Riemann sphere is, and these limits, is that sometimes what topology we're talking about is kind of implied by context, right? So the following, by itself doesn't seem to, it seems odd, right, to write this down. So limit as x goes to 0 of 1 over x, that doesn't exist, right? But if I make it z, it's suddenly infinity, right? Now, that's sort of, reading into some, some subtle context in which we're saying, well, this x, well, we always mean x is real. So, if I'm taking this limit as some real number goes to 0, I'm probably, thinking of the topology in the extended real sense, or maybe just the topology of the reals. And in which case, the limit doesn't exist, right? It clearly doesn't exist, right? So, because it goes to, if I'm going from positive x, goes to plus infinity, from negative x, goes to negative infinity. Yeah, doesn't exist, right? Okay. But z, z, well, whenever we see z, we mean complex. Okay, so this makes perfect sense, because that must be the Riemann sphere sense. Now, if something like this comes out of a blue, that might be a little confusing. Usually, there's even more context to see what limit we're doing, right? So unless it's obvious, say it, right? And unless it's obvious, I'll also say it in the book or in these slides, so that we know which limit we're talking about, right? And if you want to make it even more explicit, sometimes to say what sort of limit you're doing, instead of infinity, if you want to use the extended real plus infinity, say plus infinity, right? Right, plus infinity, and then it's always the extended real plus infinity and not the Riemann sphere infinity, right? So that's what we're going to do. Just think, in the cases when some confusion could arise, but usually it's perfectly clear, what limit we're talking about. If it's not, we'll say it, right? And even if it's clear, like if you're writing up a proof, nothing is lost if you say taking this limit in the Riemann sphere sense, right? Or in the sense of extended reals. You can always say more. There's nothing wrong with that. It's better to be verbose and clear than ambiguous. All right. Now, just like for the extended reals, we can define a little bit of arithmetic. Now, Riemann sphere is not going to be a field or a ring or anything nice, really. You can't even define arithmetic on the entire thing. And the arithmetic that you can define should make sense in terms of limits, right? So it should really be talking about, well, those kind of limits always have this value, right? So, for example, if we have some c, which is not infinity, some complex number, we'll say c plus infinity is infinity, because if I have some constant plus some function that goes to infinity, that expression will also go to infinity always, no matter what that function is, right? Now, on the other hand, infinity plus infinity or infinity minus infinity, that doesn't make sense, right? This is different from the the extended reals, right? Where the subtraction didn't make sense, but I could for example add, right? But that doesn't make sense here, right? So for example, for the addition, right? If you take z and minus z, right? Well, those both go to infinity, but if I add them, the limit goes to 0, right? Now I could add some whatever constant in there into one of them, and I could make this limit go to anything I wanted, right? Any complex number, I could make it go to infinity, right? So I could make it not go to anything. So it doesn't make sense to define these guys. Now, it does make sense to, and this is sort of, this is going to be different from extended reals in a different setting. It's actually, in terms of the multiplication, it's a little nicer. So if I have any non-zero number, including infinity, right, I can divide by 0, right? I just say that's infinity, right? So 1 over 0, I can think that's infinity, right? It's not really that, I mean, this is talking about a limit, right? So it's not 1 over 0, it's still undefined in terms of complex numbers, right? So this is, this is using the Riemann sphere, right? And similarly, if I have c and it's not 0, then c times infinity is still infinity, right? Including infinity times infinity is still infinity. That's fine. Now, if c is not infinity, so if it's a complex number, then I can divide by infinity, right, and get 0, right? So infinity over infinity doesn't make sense, but 1 over infinity is 0. 0 over infinity is still 0, right? I mean, again, it's just talking about these limits. So the thing in terms of multiplication that aren't defined, I can't multiply 0 and infinity. I can't divide 0 by 0, and I can't divide infinity by infinity. But otherwise, everything else can be defined. And again, it's really just about, what happens with the limits. That's what we're talking about here, right? It's, it doesn't give you actually any nice, really algebraic structure. It's just a shorthand for, the limit of this is this. And it's different than from the extended real arithmetic. So again, you want to be, you want to be clear if any confusion could arise. All right, so that's it for 1.3. And so next time, what we're gonna look at is start looking at linear fractal transformation in 1.4. All right, so see you next time.